Hi. In this exercise, we're concerned with a superconductor, and we're going to look at the electromagnetic response from a superconductor. And London postulated that we can use this relation, that the electric current is proportional to the electromagnetic potential. And we would like to show that in a stationary case, in a superconductor, we get this equation. And for B, we would like to determine what the magnetic field is in the superconductor. The superconductor starts at x equals 0. Given that outside the superconductor we have a constant magnetic field B0, which is directed towards in the z-axis. Okay. In order to solve that, we'll use the fact that for a stationary magnetic field, we know that the rotation of the magnetic field must be equal to mu naught J, right? From Maxwell's equations. And using the relation that we had here, we can just substitute J for this one. Or we substitute mu naught J for this value here. And then using this equation, we can just take the rotation of both sides. And take the rotation of both sides yields basically that you get this relation on the left side, and we get this relation on the right side, right? And as familiar, this is just simply the magnetic field, right? And from this side, we can use the rule that a double rotation gives two dot products and a minus sign in between them. And also, according to Maxwell's equation, this will equal 0. There's no divergence in a magnetic field. And giving these two terms. And putting them together, you get the wanted equation here, which this lambda L here is the penetration depth. And for the B question, we'd like to use this equation to solve a particular case. And we'll put in the C component of the equation, since the B will always be directed along C. And basically you get the derivative with respect to x here. And solving this equation, you get an equation of this sort. Generally you get also a term where you have a positive exponent here, but that's unphysical, so we'll, don't include that, but we'll use this part. And we know that when x is 0, the magnetic field must be equal to what it is outside, right? So A must be equal to B naught. And using that, we also finally get basically that the magnetic field is B naught C hat when x is smaller than 0, and we get B naught C hat times e to the power of minus x divided by this penetration depth. London penetration depth, that's what's it called, for x bigger than 0. Hello. In this exercise, we're concerned with the isotope effect, and we would like to calculate the isotope coefficient from the data given in this table. Here we have the critical temperature, and we also have measured the isotope mass for these different critical temperatures for this material. And basically the isotope effect is that this relation holds. Basically that the mass in the power of some coefficient alpha times the critical temperature stays constant for any particular isotope. So, taking the logarithm of both sides, we get that we have this linear relation between this logarithm of m and logarithm of tc. And using y equals to ln tc and x equals to the ln or log of m, we can write a linear relation for this isotope effect, where the alpha coefficient here, or the isotopic coefficient here, is simply the slope, the negative slope in this relation. And we can now put in a new table, which is, you can see here, which is basically, you have the logarithm of m in this in this here, and you have the logarithm of Tc here. And using linear regression, you can simply fit a line to these data points, and the best fitted line has a slope which is minus 0.45, right? So meaning that alpha has to be equal to 0.45 in this case. Hi there again. In this question, we're going to calculate what the condensation energy is for lead. And we are given a table here of measurements where at each temperature we have given a certain critical field, right? And we know that the critical field depends on what the temperature is. So for higher temperatures, right, then the critical field is lower, right? So it means that the total amount of energy is constant. Basically we're going to use this in order to calculate the condensation energy. And the condensation energy is defined as the critical field at 0 Kelvin squared divided by 2 mu naught. And in order to calculate what B naught C is at 0 Kelvin, we basically just use this relation here, right? We know that B naught is what we're given when x is 0. So we'll put in all the values here and divide BC by this value. And take the average. You can do that, or you can just do a linear regression by putting in the values for x and so forth. And then we use this to calculate the condensation energy. And what you get from this expression is this. And putting in the values, we'll get 2.74 kilojoule per meter. And again, so in this question, we like to calculate the upper limit for the resistivity in this niobium-3 zirconium. And we like to basically calculate the maximum rho from this experiment that they have done. They basically have winded a wire around a coil or around a cylinder, creating a coil where the number of winding has been 984. They measured the magnetic field before, and then they waited for an experimental time which equal to roughly 3 million seconds, as you can see here, which is equal to 37 days. And then after that they measured the magnetic field again, and then they noticed that the change in the magnetic field strength is 0.2 microtesla. And you can also see some other parameters here. You see the wire diameter is 0.47 millimeters. And you also see that the cylinder diameter is 10 centimeters. And also that the length of the cylinder is roughly 25 centimeters. So how can you from this information then calculate an upper limit of the resistivity for this thread, which is made of this substance here? Well, basically you start to realize that this is an RL circuit where basically the magnetic field in this RL circuit is can be calculated or is modeled by this expression here, which says that B naught times the exponential of minus R over L times T, basically this magnetic field here, and where the resistance in the circuit can be determined from known laws, where the length of the thread divided by the area of the thread times the resistivity gives the resistance, and also we will later see what the self-inductance is. But for the moment, we'll just point out that the length of the thread just is the number of windings, right, times the circumference, which is the diameter times pi. And also similarly for the thread area, right? It's the diameter of the thread squared times pi divided by 4. And we're now looking for the value of the resistivity, where basically after the measurement we know that there's a new magnetic field which is equal to the initial magnetic field minus the difference, and that according to the model now should be equal to this expression here, right? And now we can modify this expression, as I will show you here. We can modify the expression by looking here, and we take the logarithm of both sides of this expression here, right? So we have this expression here, we have the logarithm, and then on the other side you get this R over L times T. And the self-inductance then? Well, the self-inductance is just mu naught times the number of windings squared times the area of the cylinder, and divided by the length of the cylinder. And putting that in, as well as the area of the cylinder, we can calculate, well, basically what we do is we do a Taylor expansion of this, because we know that this expression here is very small, and doing that we can basically take away this logarithm as the first approximation, and then we will get this expression here. And just putting in the values as we had calculated before, we get a new expression, and basically from this we can just solve what the resistivity must be. And given these equations, we get a resistivity which is equal to 6.4 to the 10 to the minus 24 ohms meter. And as you can see, that's pretty low, and this must be the upper limit for this experiment.